So we're now going to move on to our final effective field theory, which is soft collinear effective theory. So what we'll do today is we'll just sort of briefly introduce ourselves to this effective theory. And by way of introduction to any effective theory, the kind of things that we should talk about are why. So we'll talk about why. And then we should talk about what the degrees of freedom are. And in this case, we'll also talk about kind of what are convenient coordinates to be using for this effective theory. So that's where what we'll start covering today. So what is SCET? So it's an effective field theory that you can use for multiple things. One is for energetic hadrons. So the energy of the hadron should be something that's a large scale, which I'll call Q, conventional notation. And by energetic, it means much more energetic than the mass of the hadrons, which is of order lambda QCD. It's also an effective theory for energetic jets. And the situation is in some ways similar to the hadrons. You have a jet energy that's large, of order some Q, and that's much bigger than the jet mass, which is the root squared of some formal momentum. And by the name, you should also imagine that really what it is something to do with QCD. Well, maybe not by the name, but it is something to do with QCD. And it's kind of what you get if you start with QCD and you focus your attention on a certain set of interactions, which are collinear and soft interactions. So we've met several different examples of effective field theories so far in the course. Some of them were bottom-up, some of them were top-down. This is going to be a top-down effective field theory, just like HQET was a top-down effective field theory. So we'll be able to start with the QCD Lagrangian and derive this theory by taking certain limits. And that's what we'll do. So why study this? Well, we'll come to that in a bit. But what are the kind of features of this from an effective field theory point of view that make it interesting? Well, we'll talk about the answer to both those questions. So first, why study this? What's this effective theory good for? So one thing it's good for is understanding factorization. And if you think about what we're doing when we probe for short-distance physics, say at the LHC, we're probing for short-distance physics by colliding things at high energy. So we're carrying out hard collisions, energetic collisions of particles. So the fact that this effective field theory deals with energetic particles may ring a bell as being something useful for understanding short-distance physics. And so what this effective theory allows you to do is disentangle the short-distance physics that you're interested in from the longer-distance physics that's associated to binding together into hadrons or producing these energetic jets. So it's really disentangling the long and short-distance physics in the standard model or the standard model plus new physics. And basically what that amounts to is disentangling long and short-distance physics in QCD. So let me write it this way. Disentangling the physics of QCD with, in addition, electroweak or BSM physics requires a separation of scales. We have to decide what's short distance, what's long distance. If we're interested in a process like the LHC where we're colliding together hadrons, then that's, of course, absolutely necessary because the hadrons are long distance things and we're interested in short distance physics. And we can do that with SCET. That's perhaps the biggest motivation for us today. When we make hard collisions, these jets and energetic hadrons are very common. They're the most common things that are produced. And from a physics point of view, that means that there's many, many different processes that you can actually use this effective field theory for, and that's one of the reasons it's popular. So let me give you some examples. You could do deep inelastic scattering with this effective theory. Deep inelastic scattering involves a hard collision. And even classic textbook deep inelastic scattering is made very much simpler by this effective field theory, and we'll show you that example as one of our examples later on. You could do Drell-Yan with either protons and antiprotons or protons and protons. You could do Higgs production, and people use this effective field theory to study Higgs production at the LHC. You could do, by way of trying to make the examples more varied, E plus E minus to jets. This is another thing that the effective theory is used for. You could do Quarkonia physics, E plus E minus, producing a J psi and an X. Here you need a combination, if the J psi is produced at large energy, of kind of a non-relativistic QCD for this CC bar bound state, as well as an SCET for the fact that it's an energetic state. So this would be actually a combination of two different effective field theories. People use it for thinking about jet substructure. So all sorts of things that you might be interested in thinking about having to do with hard scattering. There's also another way that you could get energetic particles, even if you don't force them to be energetic, and that is if you had a very heavy particle decaying. So if you had a B meson decaying and it decayed to light stuff, this would also be the right effective theory for that. So for example, in the process beta S gamma, this effective theory plays a role. In the process beta D pi, where the pion comes out very energetic, or beta pi pi, which is something very interesting for studying CP violation. You can use this effective theory to understand the short and long distance physics in those processes as well. Okay, and this is coming about because this B meson is heavy. So that's a sort of range of examples, and it's really not really complete in any sense. There's just lots of different things you can study with this theory. This I already said, but let me write it. I sort of alluded to separating perturbative physics at short distances from the non-perturbative physics at long distances. And the non-perturbative physics, if you're lucky, may be only encoded in parton distribution functions or something if you're doing a PP collision. And you'd like to separate that from shorter distance physics that you can calculate perturbatively, and this is a way of doing that. And then there's a renormalization group in this effective theory, and that renormalization group actually allows you to do something cool too, and that is that you can sum up something called Sudakov logarithms, which are logarithms that are appearing in our canonical way as alpha s times a logarithm, but instead of one logarithm, you actually get two. And so the renormalization group in this effective theory will allow you to handle those Sudakov logarithms. Okay, so That's some set of things. What are we going to have to do that we haven't done before? What are the kind of new ingredients that we're going to run into? So sort of a prelude to things to come. Or another way of saying what makes SCT different from the effective theories we've seen so far. Let's have a little list for that as well. So perhaps the most interesting one is that we are going to have more than one field for each degree of freedom. So we're going to have more than one field. That's not quite the right way of saying it. We're going to have more than one field for the same particle. Which is a slightly different statement. So we're going to have a field, which we will talk about, that I'll call C sub n, which is a collinear quark field for some quark, say an up quark. And there's also going to be another field, Q sub s, which is a soft quark field for the same up quark. So let's say for the up quark, say, just to make it definite. And the reason that we're going to have these two different fields is because they're going to describe the same particle, but in different regions of momentum space. So if you like, they're describing different degrees of freedom of the same particle, because they're in different regions of momentum space. But it still is the same particle, and that's not something we've had to deal with in any of our examples so far. We always had one field for each particle. Now we're going to have more than one. So that's one complication. This second one we have actually encountered before, and that is that we're going to integrate out off-shell modes of a field, but not the entire particle, not the entire degree of freedom. And we encountered that when we talked about HQET. So the situation here will be a little more complicated than HQET, but this second point is like HQET, and we'll use some of our experience that we gained from studying HQET.
So but if the particle is soft and collinear, which one?
It never can be both.
Why?
We'll have to decide whether it's one or the other. So an important thing, exactly this issue of which is it, is an important thing, because you're going to be describing with these fields certain fluctuations, and you don't want overlap. So you're going to have to, if you point your finger somewhere in momentum space, we'll have to decide, is it in this category or this category? It can't be in both. But that will be important, that will come back.
So you're like partitioning
Yeah, two regions and no overlap. But we'll have to work a little bit to make sure that's true. Yeah, we don't want to make sure to not have double counting in the effective theory, where we could write down something that looks like it could be described by either one. And if that was true, then we would have a problem. So another thing that makes SCT interesting from a EFT point of view is that we have convolutions. So usually in an effective theory, you think about having multiple operators that have the same quantum numbers. We sum over those operators, say at some order in the power counting, sum over I of Wilson coefficients times operators. And this sum becomes a continuous integral in SCT. We'll see how that works. And that actually leads to convolutions. In fact, exactly this little manipulation here is what leads to the convolution of the parton distribution function with hard scattering. If you think about this operator as describing, the matrix elements of this operator as describing a parton distribution function, the Wilson's coefficients is describing the hard scattering. Exactly this integral is what leads to the integral that convolutes together parton distribution functions and hard scattering matrix elements. Come back to that. So there's going to be a power counting for this effective theory. And we're going to call the power counting parameter lambda. And it's not going to be related to the mass dimension of fields. So we'll have to figure out how to do the power counting. There's going to be something called a Wilson line, which show up all over the place in this effective theory. So these are lines in space that are coupled to the gauge field A. And we'll see why they're showing up. But it's related, actually, to the fact that this effective theory has a very interesting and perhaps subtle gauge symmetry structure. One way of actually already seeing why that is true is because I told you over here that we have two types of quarks. Everything I say about quarks is also true of gluons. So there's going to be two types of gluons, an AN gluon and an AS gluon. And once there's two types of gluons, you should say, well, what's the gauge group of this gluon and what's the gauge group of that gluon? Well, they're both the same gauge group. It's QCD. So we've partitioned QCD in some kind of weird way where we have two fields for the gauge group rather than just one. Part of that story is going to be related to these Wilson lines. And finally, one final kind of interesting thing that's going to happen is we're going to see when we do one-loop calculations in this theory that we find 1 over epsilon squared divergences. So usually when you do an effective field theory calculation, at one loop you find a 1 over epsilon pole, not a 1 over epsilon squared. And I denote it by epsilon UV because both poles here require UV renormalization. We need to add a counter term to cancel this double pole. And exactly the presence of that double pole is what leads to these Sudakov logs that I was mentioning. The fact that we have these double logs going along with each alpha s. So we'll see that taking care of this with renormalization, which is a little different than the renormalization you're used to, will allow us to sum up those Sudakov logarithms. OK? So that's a kind of hint of the things that we will be studying. Not supposed to understand any of them yet unless you've studied SCET. But we will understand all of these by the end of the course. OK? Any question? Anything I missed on my list? All right. So let's spend some time talking about degrees of freedom. The way I like to think about degrees of freedom for any effective field theory is this is where you have to think about the physics of what you're doing. OK, so let's think about some physical process. I'm going to consider two different physical processes. Actually, today I'll only start talking about one of them, and then we'll talk about the other one next time. Think about some physical process and try to identify what the right degrees of freedom are. So you could look at the process of a B meson changing into a D meson and a pion. The advantage of starting with this one is that we've already talked about HQET, so we understand how to do B mesons and D mesons. We just have to understand how to do the pion. So we have a B meson. Let's think about it in the rest frame. Decays to a very heavy D meson and a very light pion. So the D meson we can treat with HQET. The B meson we can treat with HQET. The problem is this pion because it's very energetic. If you look at the momentum of that pion in the way I've drawn it, and you put in some numbers just to get a sense of what we're talking about, then it's got an energy which is slightly bigger than the momentum, and that's because it has a mass, but it's a pretty small mass. E squared minus p squared is 135 MeV squared. And so if you look at that, you see that this momentum of the pion is very close to the light cone. The light cone would be if these two are equal. That's what a massless particle would do. Pion is pretty light, and it's moving relativistically. And there's no sense in which we can think about 2.3 GeV as a small scale. We're not going to expand in 2.3 GeV over MB, because that's a pretty lousy expansion. So p pi mu here is basically some scale times a light-like vector, where n mu is 1, 0, 0, minus 1. And that's to a good approximation. You can see how good over there. So we're going to use light-like vectors to talk about particles like a pion. So n mu is a light-like vector. N squared is 0. And what we're going to be expanding in is, instead of expanding in q over mb, q of the pion, we're going to think about the dynamics with this q scale, 2.3 GeV, as being much bigger than lambda QCD. So we're going to use, for particles like this pion that are very energetic, light cone coordinates. So when you have a light cone vector like n, and you want to decompose any vector in terms of it, you need another auxiliary vector, which I'm going to call n bar. So these are two light-like vectors. They both square to 0. And the reason I need two of them is because I need some notion of orthogonality. So you should think of n bar as like the complementary vector to n. It's the dual vector in the orthogonal sense. So with those two vectors, you can decompose any vector in terms of, use them as a basis. This is how it works. My conventions. So you have two components that you can decompose along n and n bar. And the value of the momentum along that direction is the complementary vector dotted into p. And so we usually, with this notation, we call n bar dot p p minus. So that's just a shorthand. And n dot p is p plus. OK, so it's going to be useful to decompose things along these directions for the same reason that you kind of saw here, that the pion was naturally decomposing itself along a particular light-like direction. So we're going to want to do that more generally, and that's how we'll do it for momenta. If we talk about p squared, and I just square the components here, n dotted into perp is 0, and bar dotted into perp is 0. There's a non-trivial cross. This squared is 0, that squared is 0. There's a non-trivial cross term between those two, which is this. This guy can be squared. If we use our shorthand, then it's this. And if we want to use Euclidean notation, then I'll switch and I'll say that p perp squared, which is a Minkowski negative quantity, is minus p vector perp squared, where p vector perp squared is Euclidean. So sometimes I'll have use for both of those notations. All right, so I think we're out of time for today. We'll continue with this discussion of degrees of freedom next time and talk a little bit more about coordinates as well.